Okay, let's start. Today we are going to talk about hypothesis testing. Okay, so we are going to talk about two types of two ways to test hypothesis. The first one is via confidence interval, and the second one is using p-values. Okay, what are hypotheses? Okay, in hypothesis we have two types of hypothesis. The first one is the null hypothesis, which is either a skeptical perspective or a claim to be tested. Okay, so we are in scientific field we are going to test the null hypothesis because, well, we don't know the difference. Okay, see if we want to determine if there is a difference in two means, then we don't know the real difference. Okay, but what are we going to do is there is no difference. We are going to test the null hypothesis against our alternative hypothesis. Okay, this is the alternative of null hypothesis. Okay, so symbolically, null hypothesis is basically equal. Okay, and alternative hypothesis can be either less than or more than, or basically it is can be just not equal to. Okay, let's take a the skeptic will not abandon the null hypothesis unless the evidence in favor of the alternative hypothesis is so strong that she rejects the null hypothesis in favor of alternative hypothesis. Okay, so in reality we don't know there is a difference, or we don't really know the reality. But what we really do know is our null hypothesis. Okay, so we stand our ground with our null hypothesis, and we look at the data. If the data provides sufficient evidence in favor of alternative hypothesis, then we reject null hypothesis. Okay, if the evidence is so strong. Okay, so that's why we are going to use the phrase like we reject the null hypothesis, or we fail to reject the null hypothesis. Okay, because we don't really know the reality. So what we really know is the null hypothesis. So based on that, the null hypothesis, we are going to make our claim, either rejection or failure to reject. This may come to you as a little bit strange, but I think you will get a hand of it by the end of this today's session. Okay, so yesterday we talked about exclusive relationships college students have been. So we calculated 95% confidence interval for the average number of exclusive relationship they have been, that is 2.7 to 3.7. Based on this confidence interval, do these data support the hypothesis that college students on average have been in more than 3 exclusive relationships? Okay, so we got 95% CI based on our sample data. So based on this sample data, we formulate a hypothesis that a college student on average have been in more than 3 exclusive relationships. Okay, so what is our null hypothesis? Okay, our null hypothesis is college students have been in 3 exclusive relationships. Okay, so our mean is equal to 3. Okay, and then what is our alternative hypothesis? What we want to prove? What we want to prove is our alternative hypothesis, which is mean greater than 3. Okay. Now, our confidence interval tells us the range is between 2.7 to 3.7, and our null value, okay, null value, which is mu equal to 3, is in the middle. Okay, so when we are talking about a hypothesis, it is always about the population, right? We already pointed this. We already discussed this point before. We do inferential statistics because we want to know about population, not about sample statistics. So we, in our hypothesis, we always talk about population parameter. Okay, anyway, let's go on. So based on yesterday example, we have 50 college students and the mean is 3.2. Okay, and our standard deviation is 1.74, and we calculate the standard error, which seems to be 0.246. Now, what is our p-value? Okay, our p-value. Okay, I think let's go back for a moment because this slide shows the method to confirm the evidence using confidence interval. Okay, our NAR value is 3, and our confidence interval is 2.7 to 3.7. Okay, so the way to interpret is our NAR value is within our confidence interval. So if the NAR value is in a confidence interval, in a range of confidence interval, then this evidence is not strong. Okay, because the confidence interval captures the NAR value. So basically, we can say that we do not have enough evidence to exclude the NAR evidence to exclude the NAR hypothesis. So basically, if the NAR value is within the confidence interval, then that evidence is not strong enough to reject the NAR hypothesis. Okay, so in this case, we cannot reject the NAR hypothesis. But we won't say that the NAR hypothesis is true, okay? Because in reality, we don't know what is true. So we will say that we fail to reject the NAR hypothesis because there is not enough evidence. Okay, now let's come to look at how we use p-value to make this kind of claim. Okay, so basically, what is the p-value? P-value is basically probability of getting our result if the null hypothesis is true. Okay, there is a conditional probability. So if or given the null hypothesis is true, what is the probability of our mean greater than 3.2? Okay, basically, if our probability, if the null hypothesis is true, if our probability is greater than 0.05, then we were failed to reject the null hypothesis. Okay. Okay. Anyway, let's take a look at this. So based on sampling distribution, our mean, our data have normal distribution with mean approximate to population mean, and standard error is equal to 0.246, which we have calculated here. Okay, so now let's take a look at this because we want to have look at the value of 3.2, okay, and above. We want to know if the exclusive relationship is more than 3.2. So we want this upper part. So we calculated using z-score, or we call test statistic. Okay, what is our observed value, which is 3.2? What is our mean, which is 3? And then we divided by standard error. Okay, now we got 0.81. So you can look at this. There is a z-score, so we can use p-norm function in R and calculate this one. Okay. Okay, so basically our p-value, we got 0.209. So we just greater than 0.05. So which means that we don't have enough evidence to reject the null hypothesis, which is consistent with the confidence interval method here, right? So if the null value is inside the confidence interval, then we do not have sufficient evidence that we can reject the null hypothesis. Okay, next. So how do we make decision based on a p-value? So in order to calculate p-value, we use test statistics. That is also the same as z-score calculation, and then calculate the p-value afterwards. Okay, we already looked at this in our probability session on day 2. So basically, p-value is the probability of observing data if the null hypothesis was true. Okay, so we look at if the null hypothesis is true, what is the probability of having this data? So saying that if null hypothesis is true, our probability is less than 0.05, then we can say that null hypothesis is is more likely not to be true. So that's why we reject the null hypothesis if the p-value is less than 0.05, okay, which is less than 5% of probability. So if the p-value is lower than significant level alpha, okay, which is I think we first use this term now, but always remember this significant level is the same as the confidence level. Okay, confidence, this is the opposite of the confidence level. So say we want to know, previously we want to know 95% interval confidence level, then significant level is 5%. Okay, we put this value as a cutoff point, 5%. Okay, this corresponds to the 95 confidence interval, confidence level. So if the p-value is low, which is lower than significant level, then we can say that, okay, this data is not likely to observe if the null hypothesis is true, so we reject the null hypothesis. And then if it is the opposite, then we fail to reject the null hypothesis, okay, or we do not reject the null hypothesis. Okay, so here when we calculate this, we got p-value 0.209. So which means that this value, p-value, is greater than the significant level, 5%. So we do not reject null hypothesis. Okay, we do not have enough evidence to reject null hypothesis. Okay, so how do we interpret p-value? Okay, so if in fact a college student having 3 exclusive relationships on average, there is a 21% chance that a random sample of 50 college students will yield a sample mean 3.2 or higher. Okay, so this is how you should understand p-value. Okay, so our data, based on our data, we know that we know that the college student have been 3 exclusive relationships, and then we look at the p-value of getting 3.2 given null hypothesis is true. Then when we run when we conduct this kind of trial, okay, recruiting 50 college students 100 times, and then out of 100 times we got 21 times this will yield a sample mean of 3.2 or higher. So this is this sample mean of 3.2 can happen by chance. Okay, so p-value is looking at whether we can get this extreme value by chance. So we got 21%. This can happen by chance. So it's a large chance of getting 3.2. So we will say that it is this can happen by chance. So that's why we cannot reject the null hypothesis. So there is a pretty high probability. So this can happen simply by chance. Okay, so how do we make decision? Basically, if the p-value is higher than the significant level, which is the opposite of confidence level, okay, 5%, then confidence is 95%. If the confidence level is 99%, then this will be 1%. Okay, So we failed to reject the null hypothesis. Okay, and anyway, these data do not provide convincing evidence that the college students have been in more than 3 relationships on average. Okay, so the difference between null value of 3 relationships and observed sample mean 3.2 relationships can be due to chance or sampling variability. We talked about this, right? Due to sampling variability, this can happen due to chance. So that's why we are looking at the p-value, or we are testing using inferential statistics. Okay, we do not want our result to be contaminated by sampling variability. Okay, so anyway, so far we look at the relationships of college students, which is what we are looking at is more than 3.2, which is called the one-sided. Okay, we only want one direction. Okay, we want our null hypothesis is our null hypothesis is no direction because there is none. So basically, it is the neutral direction, and our alternative hypothesis is only have one direction, right? Greater than. Okay, next we will talk about two-sided tests, because in practice, when you do an RCT, this can be like, say, you are testing the standard treatment with a new treatment. So we want to look at the treatment effect should be greater than, should be greater than the standard treatment effect. So in that case, we won't be looking at any difference. We only want to look at difference greater than the standard treatment. That kind of test is called one-sided treatment, one-sided test. But normally, in epidemiological research, we usually use two-sided tests. Okay, we will look more example in next slide. So keep in mind that there are one-sided tests and two-sided tests. Okay, so often instead of looking for a divergence from a null in specific direction, we do not want to look at any specific direction. We're just interested in any divergence. So we call these kind of two-sided or two-tails, because when you draw the distribution, we want to look at both sides. Okay, and we will explain in a minute. So the definition of p-value is the same, whether you use 1 or 2, but the calculation is slightly different. If it is one tail, we only need one side to calculate. If we want two-sided, we use value from two sides of the distribution to calculate this p-value. Okay. And now, continuing our previous example, say given the null hypothesis is true, our null hypothesis is the mean is equal to 3. And what is the probability of mean greater than 3.2, or probability of the mean less than 2.8? So as you can see that we are interested in two sides, not one side anymore. So we look at the proportion. This proportion, this area under the curve and this area above the curve. And how do we calculate p-value? We calculate p-value using the probability, our probability theory. We want all this value and this value. So we basically combine this. Combine these two. So we got 41.8%. So anyway, in our example, even if we look at two directions, either direction greater than or less than, then still the p-value is greater than 0.05. So we do not have enough evidence that even the average mean is this one. Okay. So anyway, uh, why don't we write an outline how to calculate the hypothesis testing for a single mean. Okay, this is a very generic outline, so you can use for any hypothesis testing. So first, we need to set the hypothesis. Okay, what is the hypothesis? There are two types of hypotheses. One null hypothesis, which is null value. Okay, uh, this is for mean. So we write the mean symbol mu is equal to null value. If it is a proportion, then we write proportions symbol representing proportion and then null value. Okay, so essentially this null value is not always equal to 0. Okay, this is a null value. You can put any null value you want. This is not essentially equal to 0. And then we got alternative hypothesis, which can be the opposite of null value. Okay, or you can look at any specific direction, greater than or less than. And then afterwards, we calculate the point estimate. Okay, and this point estimate is always given by the descriptive statistics. Okay, you do not need to calculate specifically in this inferential statistics. And then we check conditions. Okay, we check condition whether we can use hypothesis testing because it is based on the central limit theorem. So we check conditions for central limit theorem, and we repeated this again and again. Okay, independence assumption and sample size assumption, and we check this condition. And then number 4, what do? We calculate the test statistics. Okay, in order to calculate test statistics, we need to have the observed value and the mean or any estimate. Okay, and divided by standard error. How to calculate standard error? It is standard deviation of the sample divided by square root of n. Okay, number 5, and then make a decision. Okay, because if we got v value, we calculate p value based on the z-score table or use R p norm function, and then you make a decision based on the alpha level. Okay, because it is generic, we didn't specify any percentage for confidence level. So this is very generic. If the p value is less than alpha significant level, then reject null hypothesis. If it is more than it, we do not have enough evidence. Okay, so we fail to reject it. So in order to test a hypothesis, if you want to follow the very detailed manual calculation, then you follow this step. Okay, but when we do the analysis and look at the and look at the result and interpretation, we rarely do it in these steps. Okay, we just look at the p-value and then say what is the condition, and then if the condition met, we use the p-value and then interpret. Okay, we do not. But essentially, it's a good idea to go through these 5 steps, so you will have the basic understanding. Okay, so first set up the hypothesis and then calculate point estimate, then check the condition, then okay, draw a sampling distribution, and then you can shape p-value, or essentially this calculating test statistics. Okay, we say test statistics because this is not the only test statistics. Okay, Z is not the only test statistics. For student T distribution, you use T statistics. For ANOVA and analysis of variance, you use F statistics. Okay, so there are different statistics, test statistics for different distribution. Okay, for chi-square test, we use chi-square distribution, so that is chi-square value. Okay, chi-square statistics. Okay, then the last step, you got p-value and then make a decision and interpret it in the context of the research question. Okay, let's go through a few examples. Okay, we are given this context. So researcher investigating characteristics of gifted children collected data from schools in the last city on a random sample of 36 children who were identified as gifted children soon after we reached the age of 4. In the study, along with a variable on a children, the researchers also collected data on their mother's IQ scores. The histogram showed the distribution of this data and also provided some sample statistics. Okay, so we got mother IQ score. Okay, we only have the context yet. Okay, we do not have any question yet. Okay, so we got a distribution which looks like a fairly normal distribution. Okay, so we got sample size 36, which is greater than 30. Okay, so we got a few characteristics random sample. Okay, so which our condition for independence assumption is met. Okay, this is a random sample, and this looks like a fairly normal distribution. So number is 36, so we can use the sample size skewness condition is also met. Okay, then let's look at the question. What do they want? They want us to perform a hypothesis test to evaluate if these data provide convincing evidence of a difference between average IQ score or mothers of gifted children and the average IQ score for the population at large, which is 100. Okay, so you see, we got mean. Okay, we got mean from our sample, and then they say that okay, the mean IQ score for the population is 100, okay, which is a population mean. Okay, in this case, they want to know if there is a difference between this population mean and our sample, this average IQ score mother of gifted children. Okay, so this is essentially called one-mean test. Okay, this is a hypothesis test for a mean, but basically you are comparing two means. Okay, our sample means and the population means. Okay, so let's continue looking at it. First, we need to set up the hypothesis. Okay, so our null hypothesis is always null. So we say that okay, our sample mean is the same as the IQ score of the population. Okay, that is our null hypothesis. And then our alternative hypothesis is two-sided, right? So you see, basically our mean, our population mean is not equal to 100. Okay, so our hypothesis, we got two. Now hypothesis is our population mean is equal to 100. Or we can say that our hypothesis is not, alternative hypothesis is not equal to 100. And then we calculate the pi-estimate, which is already given by this, okay, 180.2. And then we check the condition. A random 36, which is independent, and sample size is more than 30, so this is near normal sample distribution. So our assumption conditions are met. And next, we can do, we say that, okay, our data is normally distributed based on our sampling distribution, and our population mean is around 100, and the standard error should be because we do not know any population standard deviation. Okay, so we use the sample standard deviation 6.5, and then sample size, which is 1.083, and then we draw the distribution. Okay, we draw a distribution which is based on this standard deviation around 1.083. Okay, so basically, actually this is a little bit difficult to see because this graph is using the actual value from the data. Okay, so what we can do is we can look at the standard normal distribution of mean 0 and standard deviation 1, 2, 3. Okay, so I think this one is around here. Okay, and this one is -1, -2, so 1.083. So this value is 1.0. Okay, wait a minute. Okay, how do we got this value? Our mean is 118.2, but we need to calculate the test statistics. So why don't we calculate the test statistics? So we calculate the test statistics, okay? And if we draw the standard normal distribution, which is 0, 1, 2, and 3, okay, which is 1, 2, and 3, 1, 2, and 3. But our z-score is 16.8, so it should be around here, right? 16.8. So, which is basically saying that p-value is approximately very close to 0, okay? Very close to 0. Okay, anyway, when you use R, so when you find a value R, you will see that we got like 0.000 something, okay? So anyway, we will say that it's very close to 0, which is obviously less than 0.05. And you can see that, okay, which is far more than 3 standard deviation. So that is, what does it mean? It means that given our hypothesis, null hypothesis is true, then the probability of getting this 118.2 is probability is almost close to 0. So which is not likely to be true. That's why we reject the null hypothesis. Okay, so how do we interpret this? P-value is very low, so we have strong evidence against the null hypothesis. So we reject the null hypothesis. So what is the alternative null hypothesis? Which is the population is not equal to 100. Okay, so we reject the null hypothesis and conclude that the data provide convincing evidence that there is a difference between average IQ score and models of gifted children and gifted IQ score of the population at large. Okay. Okay, so next, I think let's try another example. So this example is concerning domestic cats. So a statistics student is interested in this domestic cat habit. So he took 144 cats and monitored their sleep. So they sleep an average of 16 hours per day. But according to online resources, domestic dogs sleep on average for the hours per day. So we want to find out that if the data provide convincing evidence of different sleeping habits for domestic cats and dogs in respect to how much they sleep. Okay, so he did a study. The study contained 144, which is a random sample. So we got random assumption map. 144 is far greater than 30 sample size, so we got sample size assumption map. Okay, so the mean for the sleeping hours for cat is 16. Okay, so we got one mean, and another mean is for dogs, which is 14 hours per day. So the test status is 1.73. Okay, so we set our null hypothesis, which is, I think this a little bit, it's a little bit confusing. So forget that. And our null hypothesis should be the mean of the cats and the mean of the dogs should be equal. Okay, it's equal. That is our null hypothesis. It's equal mean there is no difference between the the sleeping hours per day between cats and dogs. That is our null hypothesis. And alternative hypothesis is there is a difference. Okay. Okay, so we look at the standard normal distribution, which is 0, or center mean 0, standard deviation 1. So what is given is the test status is 1.73. So we look at the 1.73 and find a p-value. Okay, so we got two, okay, this one and this area. There are two areas. So we find one area, okay, area under the curve, this one, and then multiplying it with 2. So we've got 0.0836. Again, it is greater than 0.05. So we say that, okay, given the null hypothesis is true, our observed outcome, okay, so what is our observed outcome? That is the probability of obtaining a random sample of 144 cats that sleep 16 hours or more, or 12 hours or less on average, if in fact cats truly slept 14 hours per day on average. So if you expand, it's a little bit confusing. So you can summarize this. Okay, what is the p-value? P-value is given the null hypothesis is true, what is the probability of getting our result? Okay, so the probability of getting our result is 0.08. Okay, which is there is an 8.36% chance that this result can happen by chance. So which means that the difference between the caps and the difference between cats and dogs can happen by chance. So basically, we cannot reject the null hypothesis in this case. Okay. Okay. So this is how you look at the inferential statistics using confidence interval or p-value. So you can either use confidence interval or p-value. If the null is in the confidence interval, then we do not have enough evidence, or p-value less than 0.05 in the case. Okay. So I think the time limit is almost up, so I'm going to restart the meeting. And then next we will talk about other estimators, okay? How do we do inferential statistics for other Okay, so what about other estimators? So far we're talking about single means. Okay, so if our sample is, if we have nearly normal sample distribution, we can look at this, we can construct confidence interval for this estimator and also p-value for this estimator. Okay, so we already look at how to construct confidence interval for sample means, okay, around the sample means. Next, we can also look at the confidence interval for differences between two means, okay? And then again, the same principle applies to p-value. The only difference is there is a different formula for p, okay? Because p does not have any standard deviation. Okay, so there is a different formula for p, and also we can look at the difference in proportion, okay? Okay, anyway, when we look at the sample mean, and you can construct confidence interval. But when we do the hypothesis testing, we need a population mean, okay? We need a population mean, which is mu, okay? In this case, which is mu. On the other hand, when we got two groups, okay? So this is the mean for one group, and this is another mean for one group. And when we look at the difference, this is the same as looking at this, okay? Because we got two means from our sample, okay? So this is essentially having one continuous variable and one categorical variable, okay? But I will summarize what kind of statistics will we use for hypothesis testing tomorrow, okay? I will give you the overview of when you got Okay, which type of data variable do you got, and then you can use different hypothesis tests. Okay, anyway, this is basically when you have a continuous variable and a categorical variable with two level. Okay, like something like age and sex. Okay, so when you look at the average age between male and female, so you got average age of male and average age of female, and then you look at the difference between the two age. So it is called a two sample test. Okay, two sample test. But again, we are talking, we are discussing these confidence interval and p-value using z. Okay, z-score. But when we use the student t-test, this will be a t-distribution, not z-distribution. Okay. Okay. The idea is that z needs a larger population, okay, a large sample size. So in which case, t-distribution only requires a few sample size, and it works well, okay. But when a sample size increase, t-distribution also approximately the same as z-distribution. So basically, we use student t-test for every sample size, okay. For the illustration of the basic principle, we use z-distribution. Okay, anyway, this is the same here, okay, same proportion. So we got proportion and difference is a two proportion, and we can use the z test here. Okay, this is the inferences for other estimator, okay? So let's take a few moments and think about the bias or unbiased. So when we think about the statistics, inferential statistics, we talk about two estimator, right? The first one is point estimator, okay? Which we already talked about. When you want to catch a fish, you try and poke in with a stick, okay? That is a point estimator. You only poke at one point. So you are most likely to be missed your target. So there are two types of estimator, which is the point estimator, and second type is the confidence interval, okay? Which is also an estimator, but it is a range, okay? To capture, this will give you more chance to capture the true population. But again, when we use the estimator, the important point is we need unbiased estimator, okay? They should be unbiased. Okay, what does unbiased or bias mean? Okay, unbiased mean that the sampling distribution of the estimate, okay, the estimate, it could be mean, it could be proportion. So say sampling distribution of the mean should be centered at the true population parameter, okay, true population mean, it estimate, okay. So you call it a sample and you call it mean, sample mean. So your sample mean should reflect your population mean. If that is the case, you have an unbiased estimator. Okay, so basically, your unbiased estimator basically reflect your population parameter. Then it is a good estimate, right? If it is over or under estimate, then it is not a good estimate. The sample mean is just a sample, okay? So it could be proportion, differences in mean, and differences proportion as well. Okay, so how do we calculate the confidence interval? We can apply the general formula here. Okay, point estimate plus or minus marginal error. How do we find marginal error? How do we find marginal error? Is the critical value multiplied with the standard error. Okay, the standard error. How do we get the standard error? The standard error is the standard deviation divided by square root of n. Okay, how do we get that? We get based on the sampling distribution. When we look at the sampling distribution phenomenon, we say that, okay, standard error should be equal to standard deviation divided by square root of n. So now, using this formula, and it can be applied to nearly normal point estimates. It can be, like we said, it can be a single mean, differences in mean, proportion, single proportion, differences in two proportion. Okay, if it is a t-distribution, then this Z value will be a T value, okay, T statistics. And then if it is a F value, then it is a F statistics. But again, these are the same value. If you want 95% CI, then it is 1.96. Okay, this is not going to change. The standard error will change. And the standard error will change, and then the when you calculate the p-value, okay, when you calculate the p-value, this is no longer Z. This will be a T test if you use the T distribution. If it is a chi-square distribution, then it is a chi-square value. If it is ANOVA, then it is the F statistics. And then you look at different distribution, okay? But the same idea applies. So it is no longer it will be no longer P norm for T distribution, okay? I think it will be PT, okay, in R. And also the chi-square, you look at the P chi or something, okay? And then for the F distribution, there is a distribution for that in R. So this will be changed, okay? This value will be changed when you calculate the p-value for each distribution. So anyway, we are not going to calculate everything manually, but generally this is true for everything, okay? So you just replace with the corresponding distribution. Okay, let's take another example here. There is a 2010 Pew Research Foundation poll, and then the sample size is 1,099 college graduates, and they say that 32% watched the Daily Show, which is American late night TV show, and we got the standard error. Okay, so we got what we got is the proportion, okay, and then we got the standard error, okay, which is here, and then what we want to find out is 95% confidence interval. Okay, so this should be fairly easy, right? So we got proportion, we got standard error, and then you just say the point estimate plus or minus Z, critical value, and standard error. So you plug in this value, and then for Z, 95% CI, it is always 1.96. And now we got standard error here, so you plug in this value and say that, okay, we are 95% confidence that college graduates in US, 30.3% to 35.7% of college graduates in US watch the Daily Show. Okay, so this is how you calculate confidence interval for proportion. And then we say, okay, what about the p-value? Okay, so to calculate the p-value, we need a test statistic Z, okay? Or if this is T chi-square or F based on the distribution. Okay, so let's assume that it is Z distribution, and then say that, okay, point estimate minus null value, okay? And basically divided by standard error, okay? So let's look at this as with an example. So say we got this, the TET and NHA-NES collected fat body percentage, okay? So this is the percentage, and get general data from 13,000 population, 13,000 samples, which is a great number, age 20 to 80. And then average the body fat percentage of this one is, this is man, okay? So category is man, is 23.9%, and this value is this one for female, okay? So we got two proportion for man and proportion for women, okay? Proportion for man and proportion for women. So we got a standard error for the difference, okay? Standard error for the difference. And the question is, do these provide convincing evidence that men and women have different averages body fat percentage? Okay, so the assumption is that, okay, this distribution is nearly normal. Okay, so we got two proportion. Okay, P1 and P2. Say P1 is for male and P2 is for female. Okay, then first we need to set up our hypothesis. First, the hypothesis is the population proportion for men and women is the same. Okay, so what does it mean? Okay, it means that basically P1 minus P2 is equal to 0. Okay, it also means that P1 is equal to P2. Okay, basically is the proportion. Body fat percentage should be proportion. Or okay, anyway, we assume that it's a proportion. Okay, or what do you think? It is a mean or is a proportion? Body fat percentage. Okay,
I
anyway.
think that is a
Okay,
mean.
it is a mean.
I think so, because there is the average body fat percentage. And body fat is always calculated in percentage, and that there is a word average, so that denotes mean, I think.
Okay, thank you. So, okay, how do we do that? Okay, so this is not proportion. This is the mean. So what is that? And again, the same principle here, right? So the population. So if this equal, then if the subtract and if the different and if these two are equal, then the difference should be equal to 0. Okay, so this is the null value, a null hypothesis, and the alternative hypothesis is not equal to each other. So basically means that the mean 1 minus mean 2 not equal to 0. So basically that's it, right? So we calculated a point estimate, which is we subtract the two means, okay, which is approximately minus 11.1. And then we check the condition. So there is the normal, already it is normal, and we got large sample size, so two conditions are met. And let's take a look at this distribution. Okay, so this distribution is not standard normal distribution, it is the distribution of the real value. Okay, so that's mean is 0, and then our difference point estimate is around here. So you see it's quite far, right? Quite far from 0. And then when we calculate a z value, we got 97.36. Okay, you can draw the standard normal distribution with mean 0 and standard deviation 1. Okay, this is way beyond the 3 standard deviation. So there is p value, we will get p value almost 0. Okay, almost 0. And because p-value less than 0.05, we reject the null hypothesis, saying that these data provide convincing evidence that average body fat percentage of men and women are different. Okay, so this is how you calculate for the two differences in two means. Okay, so this is the same as differences in two means. We also use the same concept in t-test. Okay, we just also just looking at two differences in two mean, but here we use the t distribution, not z distribution. Okay, anyway, before we move on to the specific hypothesis test, we should think about a little bit about decision error. Okay, we talk about the significant level, but we still need to discuss about this type 1 type 2 error, and then how to balance these error rates. Okay, so anyway, on the left side we got the true mean, the reality, and on the right side we got the decision which we made. Okay, so the true is the null hypothesis is true, which is basically there's no difference, and the true alternating hypothesis is true, there is a difference. in reality. And then our decision is fail to reject and reject, okay? So what if the hypothesis is true and we fail to reject the null, and we fail to reject the null hypothesis? It is good, right? There is no difference in reality, and we didn't reject the null hypothesis, and then we are on the right track. Okay, and then the null hypothesis is not true. In this case, the alternative hypothesis is true, and when we reject the null hypothesis, and it is also correct, we are on the right track. What if we reject the null hypothesis when the null hypothesis is true? It is called the type 1 error, okay? Just remember, this is a type 1 error, which corresponds to the significant level, okay? Okay, type 1 error is reject the null hypothesis when null hypothesis is true. And then we got type 2 error. When the alternative hypothesis is true, we fail to reject the alternative hypothesis, okay? So these are the two errors, that are two extremes that we have to balance. Because in reality, we don't know what is the truth out there, okay? Actually, that is why we are trying to find out the truth, but we don't know. So there is a chance that we reject the null hypothesis when the null hypothesis is true. That is called a type 1 error. And there is also a chance that we fail to reject the null hypothesis when the null hypothesis is not true. Okay, this is also a type 2 error. But we will consider this possibility, which is also quite similar to the jury system, okay, in criminal court. Say no one's know, okay, say there is a crime, okay, and then we have the okay, we have a defendant, but no one know if the defendant really did commit the crime or not, okay? So we don't know. So our null hypothesis is the defendant is innocent, okay? He didn't do it. The alternative hypothesis is he did it, that the defendant is guilty. Okay, so what type of error is being committed in the following circumstances? Declaring the defendant innocent when they are actually guilty. Okay, so what kind of error will be this? When they are actually guilty, we declare the defendant innocent.
Type 1?
Actually, this will be type 2. Okay, I understand that it is a bit confusing, but bear to catch up with me. This is actually type 2, okay? Yes. Yeah. Okay, because guilty means this is alternative hypothesis, okay? When the alternative hypothesis is true, we say that this is still, we fail to reject the null hypothesis, right? So this is the type 2, and this is the type 1. So which error is more, I mean, the error are not good, okay? But which error is more, we can live with it? Which error do you think we can live with it? With type 1 or type 2? Okay, so, okay. Yes, type 1, right? Are you sure, type 1? I think we can live with type 2, right? Consider this scenario. Say, what is type 1 in this case, okay? Type 1 is declaring the defendant guilty when they are actually innocent. So we never want to commit this kind of error, okay? When someone is actually innocent, we never want to declare that person as guilty, okay? And then giving like the prison punishment. So this type 1 error, we never want to, we can never live with this kind of error, okay? But type 2 error, when they are guilty, we can, okay, we declare this person is innocent. Actually, we can still, we can still live with it. Anyway, so I think that there is a saying that I don't exactly remember the wording, but it is better to let 10 guilty men walk away than wrongly accusing one innocent man, right? Okay, anyway, comparing the type 1 and type 2, we should carefully consider about the type 1, because type 2 we can just leave as it, okay? So which error is the worst error to make, okay? Type 1 or type 2? Okay, here. Better than 10 guilty person escape than one innocent suffer. So we can never live with if we make the wrong type 1 error, okay? Okay, so what is the type 1 error rate? We reject null hypothesis when a p-value is less than 0.05 alpha, okay? So this is type 1 is corresponding to alpha level, which is 5%, which also corresponds to the confidence level, right? 95%. So which means that for those cases where the null hypothesis is actually true, we do not want to incorrectly reject it more than 5% of those times. Okay, that's why it's not a good idea to reduce to 90% confidence interval. So we want to say 95 is an arbitrary value. Why do we put 95? Because it's the balance in between these two values, okay? 99 and 90. There's no specific reason why we put 95 all the time. So you can adjust it, but you need to be careful about the type 1 error rate. Okay? And okay, in other words, when using a 5% significant level, there's a 5% chance we will make a type 1 error, but still we can kind of, okay, there will be a 100% error-free study. So we should, no, we should, but there should be still there will be still some error percentage. So we let 5%. Okay, if there is a should be an error, then we should make 5% because it is a small percentage. Okay, but 95% of the time we should capture the true value. So that is the essence of the type 1 error rates and the confidence interval. So what is the type 1 error? This is the basically probability of type 1 error given the null hypothesis is true, okay, which is alpha, 5%, which is opposite of our p-value, right? Our p-value is probability of getting the value, probability of getting the value given null hypothesis is true is equal to confidence level, right? Anyway, this is why we prefer small value of alpha. So increasing alpha, increasing the type 1 error rate. So basically it means that if you reduce the confidence level, then alpha type 1 error will increase. Okay? So we cannot live with it. So we need to be carefully consider how much we will set this type 1 error rate. Okay, choosing alpha, okay? Type 1 error rate is dangerous or especially costly. Choose a small significant level, okay? So you think that type 1 error rate is really important for your study, then you can increase the confidence limit, okay? Confidence level, or you make it the significant level small, like 1%, okay? And you will have 99% confidence interval. Okay, goal is we want to be very cautious for rejecting null hypothesis, okay? So this is especially when you are testing certain hypothesis, which is really important. Something like a clinical trial, then you need to be very careful about setting this value, okay? Not a usual, I mean, it is not the case when we usually do the routine epidemiological study. This is especially true when you consider new treatment, or you will say that something is some treatment works, okay, against the standard treatment. Then you need to be very careful about rejecting the null hypothesis when it is not true. Anyway, if the type 2 error is relatively more dangerous, okay, if your study is, if you consider type 2 error is more dangerous, then choose a higher significant level, which is 10%, okay, which is we will get 90% confidence interval. The goal is we want to be cautious about failing to reject a null hypothesis when the null hypothesis is actually false. But these are the two balance that you have to make when you decide your study. And based on these, your sample size will be different. So you need to be carefully different. You need to be carefully consider what kind of question are you asking, or what kind of result are you, what kind of hypothesis are you making, right? Okay, anyway, type 1 error is rejected null hypothesis when you shouldn't have, and the probability of doing so is alpha, significant level, which is correspond opposite of the confidence level. Okay, type 2, we call it beta. Okay, when type 2 error is failing to reject null hypothesis when you shouldn't have, and the probability of doing so is beta. And then the opposite of type 1 error is 1 minus alpha, which is good, right? 1 minus alpha, which is the confidence level. Okay, this one is the confidence level. And what is the confidence level? It is when the null hypothesis is true, we fail to reject null hypothesis. And then the opposite of beta is 1 minus beta, which is the rejected null hypothesis when the null hypothesis is not true, or the alternative hypothesis is true, which we call power of the test. Okay, so this is the power of the study, whether you can reject the null hypothesis when the alternative hypothesis is true. It is the power. So when we say that, okay, we want to test the power, when we test the power after you did the study, right? So you can only test the power after you get the result. Okay, so power testing is afterwards. But setting type 1 and type 2 and everything is before you do the study, okay, at the stage of study design. Okay, this needs to be clarified. Okay, so our goal is we keep alpha and beta low, both. We want to keep both low, but this depends on your study, what your research question, and what you want to find out. Okay. Okay, type 2 error rate. If the alternative hypothesis is actually true, there is a chance that we make a type 2 error. That is, we fail to reject the null hypothesis even when we should reject it. That is called type 2 error. And it is not obvious, right? And then clearly beta depends on the effect size, difference between joint point estimated null value, which is why we got the effect size afterwards, after we collect the data, okay, after we finish the study. So that's why we can only assess the type 2 error rate and power, whether the power we have is the power we want, or whether type 2 error rate we have is what we want afterwards. Okay, so I will quickly go through this. Okay, significance and confidence level. So anyway, when we are looking the two-sided hypothesis testing, which is 0.05 significant level, and then 95% confidence level. Okay, and then when you consider one-sided hypothesis testing, and you can see that it is more powerful because you only consider one side, and the null hypothesis is the opposite of that one. Okay. So this is 90% confidence interval with the alpha value significant level 0.05. Okay. So when we have two-sided hypothesis testing and 95% confidence interval and 5% significant level, we have two sides. So we equally distributed 5% to both sides, both here. But we only want to look at one-sided hypothesis testing. So we contribute 5% wholly to that percentage, okay? So this one is more powerful. But you need to be very careful about looking at this kind of thing. But usually this kind of test is commonly seen in RCT, okay? When you want to look at the specific duration of the treatment, okay? If the treatment is superior or not, something, okay? Okay, agreement between confidence interval and hypothesis test. So you can see that the relationship between significant level alpha and confidence level, which is 1 minus alpha, and also type 2 error, which is beta, and the power, which is 1 minus beta. So anyway, two-sided hypothesis test with the threshold alpha should be equal to 1 minus alpha. Okay, one-sided should be confidence level equal to 1 minus 2 multiplied with alpha. And then if the null hypothesis is rejected, then a confidence interval should not include the null value. Okay, we saw that in the first example that there is a null value within the confidence intervals. That's why the null hypothesis cannot be rejected. I mean, there is no enough evidence to reject the null hypothesis. If the null hypothesis failed to be rejected, a confidence interval should include the null value. That is basically the concept. Okay, so this slide is the concept, the summary, the take-home message of today's session. Okay, so null value should not be included in the interval. If it is included in the interval, we cannot reject the null hypothesis. So that is using confidence interval to make a decision. Okay, so you do not have to rely on p-value, because p-value only gives you the probability. Okay, probability against the significant level. It does not give you any duration, because confidence level gives you the magnitude and duration. Okay, how much, how large and how wide is the confidence interval. So a lot of information, but when you summarize that information with a p-value is sometimes misleading. Okay, so that's why we should not solely look at the p-value. We should also use the confidence interval to make the decision. How useful is the result? Okay, you shouldn't be just satisfied with the significant or not. Okay, and there is what is called the statistical and practical significance. I think we already discussed some point, but let's do it again. Okay, so all else held equal, okay, everything is equal, then the p-value be lower if n is equal to 100 or 100 times of that sample size. Okay, so A is sample size 100 and B is 100 times of that sample size, or 10,000. So in fact, let's look at this. Okay, so if the sample size increase, the p-value will decrease, the p-value will be lower, right? So we got a mean 50, standard deviation 2, and we got null hypothesis, and this one is equal to 49.5. And then we got one-sided test, right? Yeah, one-sided test. We want to look at the mean greater than 49.5. Okay, let's quickly look at the z-value. So when calculating the z-value, we got 2.5. Okay, for the sample size 100. When we got 10,000, z is 10 times. Okay, so which you translate the p-value, we got a very low p-value. Here, not so. Okay, so that's why the real differences between point estimate and not different value are easy to detect with larger sample. So basically, when you have a large sample size, say you have the nationally representative sample size, 10,000, then every test statistics you do, you have a very low p-value and narrow confidence interval. So that's why it is really important to say what is practical or not. Okay, at that point. So say you have 100 variable, and all 100 variable is statistically significant, and then you cannot discuss everything. You have to pick what is practical, what is more relevant. Okay. And however, very large sample size will result in statistical significance even for tiny differences, right? Because you got a very large sample size between the sample mean and null value or first size, even when the difference is not practically significant. So say something like we discussed the other day. Okay, so say we want to look at the average BMI between male and female. So the average BMI difference is only one BMI. Okay, but when we have 10,000 sample size, that one BMI difference is difference. Okay, that difference is difference, and it's going to show the p-value less than 0.0001. Okay, which is very significant. But what can you do with that BMI, right? it's barely predicate at all with one difference in BMI. Okay, something like that. Especially when we are providing nutritional support. Say you distribute nutritional support to female, okay, because you are a feminist, and then you look at the difference between two male and female, and then barely difference one BMI. So although it is statistically significant, you won't see any predicate difference. Okay, so that is how you consider what is statistically different, significant, and practically significant. So again, this is Ari Fisher, which is a very well-known, which was a very well-known statistician. Okay, to coin the statistician after the experiment is done, maybe no more than asking him to perform postmortem examination, which is well said, right? He may be able to say what the experiment died off. So that's why when we conceive or when we design a study, we should include everyone. Okay, someone who knows, some experts who know the context, and someone who is very knowledgeable, say epidemiology field, and you are doing the study, so you need statistician and other people, okay, other experts in different areas. So definitely we need the statistician.